Right, let's work on this question first. As we read the questions, we try to summarize what's going on. The first is there's 1, 2, 3. Number one, all customer insure at least one car. So that is basically the general background. So I don't feel like that offer much information other than saying percentage of at least one car equal to 1. Second sentence, number 2, 75 of the customer insures more than one car. So you can see probably of more than one car, it is equal to 0.73. 0.7. 20% of the customer insures a sports car. So that can be translated as probability of sports car is equal to 0.2. And then of those customers who insure more than one car, 15% insures a sports car. That can be written as percentage of sports car, given that this is a customer insure more than one car. That is equal to 0.15. So kind of gradually look at the information, look at the situation. So it looks like the story are trying to figure out the relation between two things. Number one, it insures more than one car. Number two, insuring a sports car. So reading English description, the verbal written description, we often end up being, at least for me, I always try to organize information in a more concise way. Lastly, the question, calculate the probability of random customer insure exactly one car, and that is not a sports. No, what is exactly one car? I guess the probability of one car would be opposite of insures more than one car. So that has to be 0.3, since at least one car. So either one car or more than one car. We don't have the probability of insuring zero car. Consider if you are the customer of the insurance company, you have to insure something. All right. So the question is to calculate. There's a keyword and in here. It says and, so it's 1 and 2. So we want to find out the probability of insure exactly one car and not a sports car. That's the question. All right, so we can kind of see this situation can be, so far I'm just writing things down, and then as we were writing things down, you can rewrite it and figure out how that can be organized even further. So one of the things we can do is, I guess the table, try to make things into a table. I need 4 columns. 1, 2, 3. Okay, so number 1 is the number of cars. So it can either be 1 car or more than 1 car. And of course, the last column is supposed to be whole. Try to organize them. And then for the other characteristics of the insurance is sports car or not a sports car. And then lastly is total. Right. So try to make a table like this. We kind of try to fit all the information into a more organized way. 1 car and more than 1 car, they are the probability. I guess I have to put into the total because that's a single event. If you have a joint event, you put it in the middle, or you multiply if they're independent. Now this is 0.3, and this is going to be 0.7 based on information. And the total probability for sports car is 0.2. So right there, we put in 0.2 and 0.8 here. And if we have any additional information, it says probability of sports car in the bigger than 1 car group is 0.115. So out of all the car, that's out of all the population that has more than 1 car, out of that 0.7, 15% is a sports car. So these two are supposed to add up to 0.7. If you want to know this one, it is a joint probability. That joint probability can be calculated by itself. So probability of more than 1 car, and sports car. So if I were to fill in something here, I have to follow the multiplication rule. So I'm gonna using the multiplication rule. The probability for more than 1 car, I know that that is 0.7 multiplied by probability of sports. That is more than 1 car. That we also know that is 0.15. And so we also apply the 2. Okay, try to figure. So it's 0.7 times 0.15. That is what I was gonna try to put in there. This is utilize the 0.15 because that is really a percentage out of a small subgroup. The subgroup is more than 1 part of 27, and then we have to do the calculation. It should have been at 0.105. Is it 105? Okay. So that's what we're going to put in here. That is the 0.105. Now, you might wonder why are we calculating this? Because what we eventually want to is to calculate probably 1 car and not sports. So it's not sports at 1 car. We need to know that spots, right? If you want to know this, you either know that or that. So now I know this, and then by subtraction, I'll know this, and then by subtraction, I can find this. I hope that kind of makes sense. Because if you want to fill in everything in the table, or if you want to find a joint event, you're going to find out something else. So out of the 4 blocks that was still empty, if you find out 1, you can pretty much using subtraction or addition to find the rest. Yes? Okay? Once we get that, and then the rest is safe. This is after subtraction, that is 0.08. Right? I'll add it to that one. And then these two are supposed to be this one, so I can then using subtraction. What is this? That is the one we're calculating. Probably one car and not spot, right? Not spot and one car. So that after subtraction, we should be able to find the answer. Any question? And that's not the only way to calculate it. I feel like having that table is like having the whole scenario. Everything is figured out. Now, if you want to calculate it directly, you have to follow the multiplication rule. This is going to be probability of one car, which we have, multiplied by probability of non-sports, given that it is one car. That one, you have to indirectly figure it out from somewhere else. Might be a tree diagram or something like that. Any question? This is the easiest way for me to think of it. Tree diagram or a table or a ring diagram kind of give us some idea of what's going on. All right, so back to this question. All right, organize information and try to understand what's going on. That is the number one thing we have to try for most of the mathematical question. Hi, Giselle, you had a question that I kind of pushed the day to today, so we can finish that one. I think it was the 11 and 7 on the 1.3. So maybe we should talk about it in class together. That way, number 7. So let's try together. Box 221 yellow and 730 red. If 15 jelly beans are selected at random, what is the probability that the 11 are yellow? Okay. All right, so we can then first look at the total. Yellow is 21, and then green is 27, and red is 28. So then the sample size total is 48 plus 676. At least on my version. 76. Okay. Now the first question is we're choosing 75. So we really are doing 76 choose 15. That's the overall the denominator. That's if you don't care what was the one that you chose, and then you're doing 76 choose 15. Now the question is what is the probability 11 are yellow? And so how do we have so 11 yellow out of 15 are selected? Oh. Change the view. The overall setting is choose 15 of them. So your denominator should be 76, 15. In the numerator, you are looking at detail, which one is chosen, which one is not. And out of that 15, if 11 is yellow, what about the other 4? They can either be green or red, right? So there are a couple of different information. I kind of understand why this one can be complicated. So the total is 21 yellow, so we are gonna choose 11 yellow, 11 choose 21 choose 11 yellow, and then so how many of the other one you have a bunch of choices. To decide on what happened to the other four. So for the other four, it could be all four of them are still three different choice, right? So let's go ahead to right. Okay, so this probability 11 are yellow. So there's no more 11. So then there's no more yellow. So 11 yellow. That means the other four are either green or red. So we could have 4 green. So that's 27 choose 4. This is all green. Or you can have 3 green. 27 choose 3 times 1 red. That's 28 choose 1. So 3 green, 1 red. Or kind of involve all the combination. Or 2 green, 2 red. So that will be 27 choose 2. And 28 choose 2. You can also have 27 choose 1. There's 1 green and then 3 red. Throughout the space, there's 1 more, right? What if the all red? Yes. All the combination. So I can think of it as a numerature problem. What is space? Right. There's one last scenario in the numerature that we have to add. That is 28 choose 4. All 4 of them are red, and this is all the possible combinations in the numerature. Question. Okay. So let's try that. Have you tried first one?
Yes, but since I don't wanna, I can just put in C, like choose that, but I have to put the numbers and so I just have to go back and put like.
Okay, yeah. We can put it in calculator and find the answer, then we put in the final number. So the number should be 76 choose 15. Numerature, what it is, 21 choose 11. Being multiplied by, it's kind of tiny on the screen. Yes, I should type it out so you can actually visually see it. Because it's very small. You can actually see it. And then the numerature goes 27C4. Well, with a calculator, it should be a. You multiply by 7 choose 3 times 20 plus 3. Choose 2. These are all the ones I tried to calculate the combination number using the Google calculator. What the heck? So small. Yes. Calculation law. No. One, two, three, two, one. This one should be one. This one should be records my only 6. Okay, so I think the calculation scheme is right, except that I added one the wrong number there. That's the first question. The second one should be calculated as there's no change to the denominator. Numerator is 11 are yellow, 3 are green. This one is not that general. It's very specific. So the denominator is still going to be 76, choose 15 of them. Then numerator is the one I need to calculate carefully. There's 11 yellow, so you have out of the 21 yellow, you're going to choose 11 yellow. And then 3 green, so the 27 green, you're going to choose 3. There's only one left. That one last one that's left has to be red, right? Because the colors identify. You can't have one more yellow or one more green. It has to be red. So 28, choose 1. That's really how we calculate the part B. So the calculation should be more specific. Okay. All right, so that's easier than the first one. I mean, the more general, the less. The more possibility we have to consider. So 11 that, so we will have the, let's see, green is 27. We're going to choose 3. So 27, choose 3. And the last one is 28, which is 28. That is the calculation. Into our calculator. It's even smaller because we have a less scenario. The denominator is really large. I mean, choose 76, choose 15. There's really large denominator, which calls for fraction to be super small. And that will be the answer for part B. Any question? I just go have a calculator from the calculator. If you need your help from your version of it, if your number seems to be tricky, I can work with you. Any question? All right, last question. Last question is, what is the probability at least one is yellow? That means 1 yellow or 2 yellow or 3 yellow. It could also be 21 non-yellow, no 15 yellow. So it's the type of at least 1 in yellow. So what is the opposite of at least 1 yellow? That is when there's no yellow. So it's easier just to go ahead calculate probability of no yellow and do 1 minus that. But even if we wish to calculate no yellow, that means the 15 of them could be green or red. That is still a whole lot of scenario to consider, right? The numerature is really large. So there we have it. So let's go ahead and calculate it. The denominator is still gonna be 78, choose 15. Now the numerature, we are no longer consider yellow and only consider the green and red. We got 27 green, 28 red. So the green is 27 and the red is 28. Just want to get that number there. And we're choosing 15. Okay, so it could be 27 choose 15. So all 15 of them are green, or 27 choose 14. So 14 of them, yes.
Since the order doesn't really matter, could you just do 76 minus 27 and then do just like that, choose 15 instead? Like, trying to think. Like to subtract the number of the other color of yellow, and then you just put that over, choose 15. It's a combination.
Yeah, the order does not matter which one to choose, but do you mean well, how do we calculate?
Like Ryan did. Right.
You already tried it?
Yes.
Okay.
So
Let me grab my glasses.
mine is it 9 or selected and 25 are yellow, so if you want no yellow, if you subtract 25 from the total and choose 9, put it over.
Okay. Okay, thank you. That's nice. Yes, so if we don't care about the color, so then green and red together is 27 plus 28, which is 55. All right, so we really are choosing 15 out of those 50. So it's 55. 50, right? We choose 15 out of the 55. We don't choose anything from the yellow, but green or red doesn't matter anymore. So this is a probability of choosing no yellow. And of course, you're going to calculate choose at least one yellow opposite. So 1 minus this division will give us the answer. So then for the last question of no yellow, thank you. This is a lot easier. I was gonna go this many red, this many green, this many red, this many green, and then do a lot of multiplication and summation, multiplication and summation. Your idea is a lot faster. So let's put that into a calculator. That's very likely to be no yellow. Let's take the probability large. Let's start it back. This is a question number 7. Try it on your version if you still have a problem. Did it work?
But I'll probably figure it out. I think my numbers. But I helped explain.
Okay. Number 11. This one, I'm not sure mine is the same as yours, but this is the example. A variable is tossed 3 times, and then ABC represents at least 1 head is observed, B at least 2 heads are observed, C is the number of heads observed is odd. So the first question is to calculate probability of not B, not B. Question 11. So we will calculate B first in order to calculate not B. Probably. If you toss a coin 3 times, then if we use X to represent number of heads after 3 toss, then X can be 0 heads, meaning they're all tail, or 1, or 2, or 3. So that's really what it is. The number heads can be that way. So then at least 2 heads means 2 or 3. So then we would calculate the probability of B will be probability of X equal to 2 and the probability that X equal to 3. So let's calculate it one by one. What is the probability to get 2 heads out of 3 toss? All right, we can try to look at how it is if you toss the coin 3 times. Head or tail, head or tail. First toss, second toss, head or tail. And third toss, head or tail, head or tail. Head or tail. Following each pass, we can kind of see what it is. The first one is they're all heads. The second one is head, tail. And third one is head, tail, head. And then there's head, tail, tail. Head. So, all right. So this is equal or likely 3 different outcome, 8 different combination process 8 times. And you can see how many of them having 2 heads. They are 2 heads. There's 2 here. There's 2 here. This is the probability of having 2 heads, right? So then the probability is 3 over 8. X equal to 3 heads. That's the first one, and that is really 1 over 8. So altogether, it should be 4 over 8. And then make it 1/2. So the probability of not being, it should also be 1/2. This is kind of useful for choosing the possible outcome. If you do something 3 times, then equally likely at every trial. This is A. Second one is to get probability of A and B. A is at least 1 head. B is at least 2 heads are observed. At least 1 is at least 1 means is 1 or 2 or 3. Now at least 2 means 2 or 3, right? So if you want A and B, it must be 2 or 3, right? It should be the same as the B if we think about it. So when you join them together, I think it's the same probability, so the answer will be 1/2 as well. Last one is A and B and C. C's number had observed is odd. So if you want A and B, you have 2 and 3. But if out of C you want it to be odd, it has to be 3. For probability of 3 heads, we have 1 over 8. So the last one, the answer must be 1/3. Any question? You might have to look at your version because there are different choices for A, B, C. We may not have multiple question. Just is your question the same?
Most of it was.
Okay. And let's check. 1/2. Any other more questions? So try it. I reopen this one. It's open till tonight. So let's try to get it done. All right, I think 1 through 5 finished chapter 1. That is general probability topic. And then we will be on specific probability model. Now, probability model can be discrete or continuous. Have you guys heard of discrete? The word discrete. Okay. Discrete versus continuous. These are two possible type of numerical data. If you have quantitative, like qualitative data, then normally they can be considered a similar model to the discrete type. But most of the quantitative data, they're either discrete or continuous. So let's start with the discrete model. The whole chapter 2 having different type of model of the discrete data, discrete probability model. And then chapter 3, we focus on continuous probability model. Let me turn this off. The voice is muffled a little. I try not to wear it, but I feel like when I was wearing it, somehow I cough a lot less. So I end up wearing it, forget to take it off. But in the classroom, I always worry a little that this week, especially, I cough too much. All right, let's start with 2.1. Let's look at discrete probability model. All right, 2.1, the title is called random variable of discrete type. Okay, now in mathematics, we deal with variable all the time. Variable, the root word is vary, and something change. So variable is really a quantity that changes the value. Like x equal to 2, x equal to 3, x equal to 5. That's when the variable x takes on different value. Now, what do we call random variable? Is quantity that could take on different value for unexpected value. I mean, you don't know what's the value until you run the experiment and you discover the value. So that's why it's called random variable. This is specifically only in probability and statistics. In other classes, we only have variable. We don't have random variable. We call it random because it's not predictable. Discrete type is the kind of variable that has to be counted. So you can 1 by 1, 1 or 2 or 3. And there's no 2.5, there's no 2.1, that kind of data. For example, number of person has to be counted 1 by 1. Number of cars, we really have a force of the car. So number of car has to be a variable of different type. Number of mistakes, we say we made 1 mistake or 2 mistakes. We generally see I made a half of a mistake. There are always things that cannot be continuous. It has to be discrete. Right? So those are definition for a random variable. So since we're calling the variable, it has to be something that we have to measure, have to count. So there's something is based on certain experiment. If you run an experiment and you will be able to figure out how many possible outcomes and put it together as your sample space. But random variable is not the same thing as the outcome in your sample space, because random variable is something that interests you and you want to actually calculate. For example, for the same experiment, you can record different things as your X value. For example, you toss a die, the outcome is 1, 2, 3, 4, 5, 6. But the X value It doesn't necessarily has to be the outcome number. It could also be x equal to 1 if the outcome is odd, x equal to 0 if the outcome is even. So the x value ends up being recording the odd or even behavior. Even more, for example, we know if you toss 2 die, you have 36 different outcomes. But instead of looking at those 36 outcomes, maybe you don't care what was their individual. You just want to know the summation. So x will be the sum of the points after you toss 2 die. So x is a random variable. It may not be exactly the same as your sample space. So we were saying that knowing the sample space is helpful when you try to calculate probability. But when you're defining a random variable on top of your sample space, on top of your the experiment, you have to focus on what was the definition for your random variable. So that's together with the experiment, you're deciding what is your random variable definition, is the reported value for the random variable. So this is a question that we mentioned again and again. You toss the die, 6-sided die, the outcome is 1, 2, 3, 4, 5, 6. Now the random variable can be, let's say x, the random variable is s, which is the number outcome. In that case, there are 6 different values for x. So probability x equal to 5 is 1/6. That's 1. All right, so I was trying to talk about the random variable thing. That is, number one, for this one, we're assuming the probability for 1, 2, 3, 4, 5, 6 is all 1/6. But in a actual practical situation, it may not be on. It may not be given. For example, how do you know it's 1/6? Maybe it's more likely to be one of those numbers. Number two, what is the x value you're recording? What are you interested in finding out? And that is the actual function we have to look at. So when you actually try to make up a model, we're modeling the x. So you have to define the x, be specific what x exactly is as you go ahead try to determine the model or the underlying distribution. All right. And also, what we already mentioned is what's the discrete, what is continuous. A discrete model, it means that the number of points or the number value for x is countable. You can count it one by one. So you can actually, the way of saying when something is countable, the number outcome can be counted, can have a one-to-one correspondence with a integer, such as 1, 2, 3, 4, 5, 6, and so on. Any question? I mean, the way I differentiate discrete and continuous model is if it has to be counted one by one, it must be discrete. If it's measurable, if it's continuous, normally it's measured, data measurable. So it is allowed to be a fraction or a decimal, then it must be continuous. All right, so we're going to try to find out how do we model a random variable, and we're going to define something that's called a probability mass function. Probability mass function, and that is for each value of the x, we give it a probability model, and that means no matter how many x value you know is going to happen, you have to find the probability for it. So basically, you would have a list of probability value for each x value it takes out, and that's going to be our function or EMF. So this f of x is defined as a probability for x takes on the function that takes on the value x. So then this f of x is the probability value for the random variable x. So f of x is a probability number. That's why it has to be a number between 0 and 1, so it has to be positive. The summation of all the probability value has to be 1. So these first two properties, A and B, those are the probability we already have, the property that we already have for probability. And the last one saying that if you have an event, probability for event A is summation of all the probability within it. So this is how we deal with the probability calculation involved with X. Let's try to make an example of this, what we are talking about. For example, the most common one we already mentioned, that if you toss a die, then six-sided die, and let's say the X value is the outcome, is the points on the die, then X is taking on 600. So X can equal to 1, 2, 3, 4, 5, 6. And we do have a model. And sometimes I call it P of X. You can write F of X. F of X is probability, defined as probability that the random variable X takes on the value X. And according to our model, if the die is a fair die, let's add that extra requirement. Assuming this is a fair die, then this probability must be 1/6. So that's true for all X value. So meaning the probability mass function equal to this for all the possible X value. So X equal to 1, probability 1 equal to 1/6, probability F of 1 equal to 1/6, F of 2 equal to 1/6, and so on. And this is using function notation to define the probability mass function. So this is an example of the probability mass function for X. So our PMF. You can also derive a table to get a table for your probability model. You can see that the X value can take some 1, 2, 3, 4, 5, and 6. If it's uniform, if it's a fair die, then the probability is a mass function. It's 1/6 for each one of these. So it's 1/6 for every one of these. I mean, of course, if the die is not fair, then some of these values may not be exactly 1/6. But this is, so you can see that the function notation is the same, has the same meaning as this. Sometimes when it's discrete, I actually prefer to use a table. This is visual, easy to see. Right, and that kind of go with all the idea that we had, and like all these probably has to be bigger than 0, and they all added together equal to 1. If you want to find some of them, you have to add it. For example, this question: what if I want to find what is the probability that X is less than 3? I want to find this, then the probability will be 1/6 plus 1/6. Because for it to be less than 3, there are 2 of them. So it's 1/6 plus 1/6, which is 2/6, or 1/3. And that's just the example for the part C. Part C says, if you want to find probability of the event, you have to add up all the probability within that event. Question. Just want to illustrate how this definition can be applied. All right, and let's talk about CDF. This is in comparison with the PDF, PMF. PMF is representing probability mass function. Now CDF stands for cumulative distribution function. So cumulative distribution function is more important because it allows us to find out what is the probability for the variable to be lower than the certain number. Any question? So for example, the one that we were writing out. So then for this question, we use capital F of x, which is equal to probability that the x is lower or equal to x. I mean, we use capital X for the variable, but then the lowercase x is for the value. Right, it takes some. Right, this is going to be a little hard to do because you see for different x value, it's an increasing order. What is this exactly? See if x equal to 1, that will just be x lower or equal to 1. That will just be 1/6. If x equal to 2, that's below or equal to 2. That will be 2/6. If x equal to 3, that will be 3/6, right? All three will add together, right? The same pattern follow for x equal to 3, 4, 5, 6. For 6, it will obviously be 1. But then again, then if you summarize it, we realize we can write it this way, which is x/6. And then x is equal to all that number. I mean, if it's 1, it's 1/6. If it's 2, 2/6. Obviously, you can use a little formula x/6 for the cumulative distribution function. So the probability mass function is f of x equal to 1/6 for all 6 values. The CDF is f of x equal to x/6. That's the cumulative distribution function. So then it's the formula way. And of course, you can come up with a table for it, but I normally only make a table for the probability mass function, not for the cumulative ones. Cumulative ones, if it's possible, I would prefer to use a formula. Any question? Again, we can graphically display, for example, the probability mass function. You can graph it like this. Not the best way to do it, but this is 1/6. But it takes on 1/6 for 1, 2, 3, 4, 5, 6. 4, 5, 6. So that we can use a little bar. So 1/6, 1/6, 1/6, 1/6, 1/6. So we can graphically display the probability mass function. You can do the same for the probability for the CDF, which is going to be this. There's going to be an increasing order there. So the CDF and PMF, we're still calling it a probability mass function or probability cumulative distribution function. They're still a function. So they're still representing a correlation between input and output, except this time the input is your random variable value and the output is a probability value. Now, and the way we just did is typically called a discrete uniform distribution. For our case, m equal to 6, and that's 1/6, because it's equally likely to be any one of the number between 1 to 6, which is why it's called a uniform distribution. And we did talk about this one. The CDF for the uniform distribution is x/m, or x/6 with the toss die problem. That we have definition, have answers in the book. Just want to summarize that. And for example, this is an example of roll a fair 4-sided die twice, and then the outcome will be 4 times 4, 16 outcome. X equal to the larger of the two outcome. If the larger one of the two outcome, then X takes 1, 2, 3, 4, obviously. If the two are both equal to 1, the larger one is 1. If the two is 1, 3, 1, 4, the larger one would be 4. X representing the larger one of the two outcome. If you're tossing fair 4-sided die. Now we're going to try to come up with a model for the X. So sample space is going to be a pair of die. The sample space on B is going to be 1, 2, 1, 3, 1, 5, 1, and so on. 16 of them, 4 times 4, 16. But X representing X can only be 4 number, right? The larger of the two, 1, 2, or 3, or 4. So we want to come up with a model for the X. Now, so we can actually try to think of what is the possible outcome. It's very easy to identify it if you already have the entire sample space. And let's see. This is our XY plane. Okay, this X represents the first die, and Y represents the second die. It's 4-sided die, so X can be 1, 2, 3, 4. All right, and then the Y, which is the second die, can be 1, 2, 3, 4. We're talking about 2 die, right? 2 4-sided die. So the outcome can be 1, 1, 1, 2, 1, 3, or 1, 4. It can also be 2, 1, 2, 2, 2, 3, 2, 4, and so on. Basically, there are 6 outcomes. The combination of the outcome is this. This is a possible outcome. But then we're going to look at how many of them have the X being, X is a larger one of the two. So X equal to the larger one, the 2 after you randomly toss it. So how many times that X equal 1? Let's calculate that probability. If the larger one of the two is a 1, that means both of them has to be 1, right? If any of them is higher than 1, then the larger one's not going to be 1, right? So there's only one of them, which is going to be that one, 1, 1. So out of 16 total outcome, only one of them allows the X to be a 1. So in this case, the probability has to be 1/6. 1/16. All right, and then the second question, what is the probability X equal to 2? Again, the denominator would be 16, but we're going to find out how many times the larger one of the 2 is 2. This one, like if you got 2 and 1, the larger one's 2, right? But if it's 1 and 2, the larger one is still 2. Right? It's right. But what if it's there? It's the 2, 2, then that's, if they're both 2, the larger one is still 2. Yes. So that means we got 3 of them. 1, 2, 3. So it's going to be 3/16. So we can gradually see some pattern. Next one, what is the probability for the larger one to be a 3? Okay. Again, denominator is 16. The numerator is the one we look at our whole sample space. The larger one to be a 3. Anything that involves 3. So this one, 1, 3. The larger one is 3. 2, 3, 3, 3, right? And then that's 2, 3, 3, 1, or 1, 3. So I think this is all the one that has a larger one being the 3. Altogether is 5. Okay. Now leave the only one outcome. If for the larger one to be a 4, any time a 4 shows up in any of the outcome, X equal to 4, which is all the one that's left over. That is 7. So it's 7/16. Okay, so that is our entire model for the probability X function. Yes. So we could simplify it. Instead of calling it P of something, we make it short. We say f of X, which is representing the probability math function. F of X representing probability that X is equal to X. The random variable equal to X. We could come up with a formula for this. The denominator is 16. Numerator is sequence. And somehow you have to be in charge of come up with a log. But the sequence first number is 1. The increment Is 1 to 3, 3 to 5, and 75. So the increment is 2, right? Increment is 2. That indicating that it's a steady increase, a linear increase with slope 2, right? Because so it must be 2x. So one of the 2x, and it starts from 1. So if x equal to 1, 2 times 1 is 2. We have to minus 1, I guess, right? And let's see now if it fits the model. If x equal to 1, 2 times 1 minus 1 is 1. If x equal to 2, 2 times 2 minus 1 is 3. If x equals 3, which is the third one, x equals 3, 2 times 3 minus 1, which is 5. It seems like the 2x minus 1 is fitting all the numerature that we have right now. So we're using a linear function to finally represent all those quantity. Another way to look at it is also to realize that 1, 2, 3, 5, 7 is the first 4 odd number. So if you think about how we represent odd number, we can use 2n plus 1, 2n minus 1, or 2n plus 3, or 2n, and so on, right? Depending on which number you start with. Since we start with 1, we're using 2x minus 1. That's our model. And then again, we're not making it general. We're only allowing 4 number. So x is equal to 1, 2, 3, 4. That's all the possible x we have. And that's the domain of the function. Okay. So this function is 2x minus 1, but 2x minus 1 is representing a line, which involves a lot more number. But now we specifically only want 4 points. So out of the entire line, we want 1, 2, 3, 4 as our function value. Any questions? Okay, so this is giving a formula, or this is giving a list. It was a list. You can actually make a table if you wish. And you can also draw the graph. And the graph can be drawn with a vertical bar representing the probability, or you can also use a point graph, like 1 over 16. So x and y, 2, 3 over 16, 3, 5 over 16. You can use point to represent the relation, whichever way. But since this is a function, we have multiple ways to visually present a function on the xy plane. And most of the time, we try to figure out a way to visually understand. So this is our probability model, and that's what's presented in the text. All right. So we representation of the probability mass function. We can use a probability histogram or a bar graph. Okay, so over here is the same thing that we mentioned earlier. You can use a bar graph. This is a histogram. Histogram is connected bar graph, and this is like a single bar with no weights, and that only represents this, making it more discrete. But then people feel like this is a lot visual, like visible. So either way is okay. These two graphs are actually presenting the same thing. Any question? This is 2.1. The main thing is to introduce the idea of discrete model. And you can have a table to represent a discrete model, it's discrete probability model. You can use a formula like f of x equal to 1 over 6 to represent your probability model. Or you can use a graphic display. And yeah, are we out of time? We have 10 more minutes, right? Okay. Let's talk about what can we do when you already have a probability model that is 2.2. Now, we want to be able to identify some of the features of the distribution. That is, we can find out the central distribution or the standard deviation distribution. Okay, and this is really following the textbook. I feel like it's a lot of things to read through. Okay, there's a little background. I was worried about the timing. We only have 10 minutes left. You know, we go to finish the whole thing. So this is a game about using a fair die. You receive a payment according to the outcome of the fair die. If you got 1, 2, 3, you receive $1. If you got 4 and 5, you receive $2. If it's 6, you receive $3. So X representing the number of dollar amount, it's either 1 or 2 or 3. Okay. And so now the question is, what is the average number of payments? So after we read through the question, I hope we kind of understand what's going on. So this is a game. You toss a die. Obviously, if you toss a die, there are 6 outcomes. So you receive $1 if it's 1, 2, 3. But overall, we have 6 outcomes. Right? So that makes it 3 over 6. 3 over 6 probably. Now you will receive $2 if it's 4 and 5. That makes it 2 over 6 of a chance, like smaller chance. Now if you toss it and you receive $3, it looks like everybody's winning, right? At least you receive something. If it's 6, and 6 is on, it's not as likely, but it's still 1 over 6 chance. Now, that is our probability model, right? That is our probability model, but sometimes we wish to find out, on average, how much do we get? So it felt like out of the 3 outcomes, the 1 has the biggest probability. So if you want to find the average has to be kind of like finding the average of the X. What is the average of X? It certainly is not 3 because 3 is less likely. The one more likely is 1. But I'm guessing the average of 1 is around 1. But we wish to make a more fair calculation. So how do we calculate it? We can use the probability as a way to calculate a weighted average, right? The X value can go 1, 2, 3. So we are averaging 1, 2, 3, but they're not equally likely. So the average is not 2, right? We're not adding it together divided by 3. If we're adding 1 plus 2 plus 3 divided by 3, we will be getting 2, which 2 is in the middle. So we're calculating something called expected value for X. The calculation, it is actually a summation of the X value multiplied by the probability value of each one. And that is the expectation of the X value. Actual calculation for this X value is calculated by the X value equal to 1 has a probability of 3 over 6. Now the probability, the X value 2 has a probability of 2 over 6. And the 3 has a probability of 1 over 6. Each X value, there's 3 of them, has to multiply by their probability, and then we add it all together. This total summation is a weighted average of X value, and if you put it in a calculator, you see it is more leaning toward 1, higher than 1, because we do have something higher than 1, but it's definitely more closer to 1, since the 1 is heavily weighted in the entire probability model. I got 1.667. So then that's the calculated. Well, it's actually 1 and 2.5. 1 plus 2/3. And that's something we wish to be able to calculate if you already have a probability model. And this is everything, the main idea over here. So I just want to finish this one. That's the number, right? That's 1 and 5/3 is the same thing as 1 and 2/3. Let's finish it over here because the rest needs a lot more reading, more example. In the meantime, I already assigned the assignment for 2.1, to we'll wait until we finish. And that will be for today. And I guess I'll see you next Wednesday since we don't have classes on Monday. Thank you. Call this time and think I'm getting better. See you next week.